So you see, we have started studying the many body quantum system, which is our atomic nucleus, right? Now we have done a lot of mathematics, and each time I have also discussed about the physics behind this system. Now you see, you remember when we are writing the Hamiltonian, then in the Hamiltonian, just there is a term, kinetic term, right? And then there is a two-body interaction. Now I am again approximating the effect of three-body, four-body are negligible. So effect of only two-body interaction. Next, what did I do? I added a single body potential, one body operator, and subtracted the one body operator. And then addition of the one body operator to the kinetic term, it made the H0 or the mean field. And then the separate part, two body minus one body potential, one body operator, that is known as the residual interaction, right? Now, in the most basic approximation of the cell model, what we did was, most basic approximation was, we choose the one body operator in such a way that this H1 becomes negligible, right? And then what? Then the entire Hamiltonian is just equal to H0. So what does this mean? This means that now this atomic nucleus, quantum many-body system, this consists of basically non-interacting protons and neutrons. This is the meaning. And a single proton or a single neutron is basically moving in the mean field created as a result of all other nucleons. So this is the basic idea. And also remember, regarding the strong interaction, there is not much difference between proton and neutron. But there is a difference due to electromagnetic interaction. One is charged, another is uncharged. Okay, now we will still be feeling the protons and neutrons independently in this part, in this basic shell model, which you may call single particle cell model, non-interacting cell model, and all that. Now after that, this comes the next part. Here, what we will do is, we will consider the effect of this H1 residual interaction. Why? Why do we need to consider the effect of residual interaction? Let me just show you in this part of diagram. If you consider the level scheme of 18 oxygen, now if this is the experimental level scheme, the experimental level scheme, I am not showing the energies. This is the energy. Okay, energy in keV. Now if you observe the experimental level scheme, then the level scheme looks like this: 0 plus, 2 plus, 4 plus. Now you remember in 18 oxygen, just after the 16 oxygen core, there are only 2 neutrons. Those 2 neutrons go to 1d 5/2 level. Right? Now using the M scheme, I have shown what are the possible angular momenta. Only 3 angular momenta: 0, 2, 4. Fine. Now look into the experimental spectrum. What do you see? The first thing that you see is that the energy of 0, 2 and 4 are different. So, now, but just now I told you that if we have 2 neutrons in the 1d 5/2 level, the corresponding spins will be 0 to 4, and they will be degenerate. But the very fact that they are non-degenerate, and look into the order of the spins, there are 2 very important information. এই কথাগুলো কিন্তু লিখে নেবে পরে. It is not possible to write all this stuff in the blackboard, but you please write it down. Okay. So there are 2 very important information. Number 1, the 3 spin levels are not degenerate. Okay, they are not degenerate. Look, they are different energies. Number 2 point. So that was number 1. Number 2 point. Look into the order of the spins. The 0 plus is much lower, 2 plus is above, 4 plus is more above. বুঝতে পারছেন? So now, how do we try to understand this structure? Remember what we have done here. We have forgotten the very presence of H1. So let us now take this into account, H1. Now, how do you take into account H1, residual interaction? The most basic way of introducing the residual interaction is to consider that suppose two nucleons, say two neutrons in the J is equal to 0 spin. What will happen? One will move like this, another will move like this, opposite direction, right? And so in each orbit there will be 2 times that they will meet each other. This is a classical way of thinking, but again it is very helpful. So this means that there is this way. Now what about J is equal to 2 case? In J is equal to 0 case, the orbits will be the same, but in J is equal to 2 there will be some angle. In J is equal to 4 the angle will be even more. It means the overlap will change, right? So J is equal to 0 case will have maximum overlap. Now maximum overlap means maximum interaction. So this could be a way to understand the ground state spin of why it is so much depressed compared to 2 plus and 4 plus. You understand this thing? So now what we do, we consider just the residual interaction V is equal to sum minus V0. So let me take this residual interaction is equal to sum minus V0 constant into a delta interaction. Delta interaction means whenever the nucleons come very close to each other within a certain distance, then they will be attracted to each other, and there is nothing else in this. Now if I do this is the basic concept of introducing the pairing interaction. You remember in the class that we worked this out mathematically, and amra ki dekhlam, what did we observe? What we observe is that in V we can explain this thing. So let me run this part. Okay. But still here we have H is equal to H0. So if I now take this into account, just the effect of pairing, okay. So what we will observe is something like this: 0 plus, 2 plus, 4 plus. Again, equinoxy. Now look into the spectrum. So at least now we are able, okay, now at least we are able to get some non-degeneracy. So 0 plus is much more depressed compared to 2 plus and 4 plus. ठीक है sir? So understand this thing. But again, this is not the experimental spectrum. So we are missing something, of course. What is that? Now you see, when we were doing this calculation, we were just considering 18 oxygen made up of 16 oxygen core, and the 2 neutrons, they were just in 1d5 half. Now is it a logical step? It cannot be fixed to just 1d5 half. There are so many levels above, 2s half, 1d3 half and all that. But in doing these calculations, basically I have considered the valency space to be just the 1d5 half level and ignored all the levels above and also the core levels below. I have just considered this level. Okay, and as a result I have gotten this. Now, in order to improve the model, you have to understand what we are missing. Let me tell you. You see, when we first started doing the calculations, you must remember we wrote like this: H side is equal to E side, right? And later on we decompose this to H0 plus H1, and then I introduced a new set of wave functions. Remember what they were? They were phi. and they were basically eigenfunctions. These 5 were eigenfunctions of the core wave function. But this psi is basically the eigenfunction of actual Hamiltonian H0. Now we have to solve this entire problem with psi, but we do not know psi. Why? Because this is unknown. We do not know the nature of this. So to make life simple, we have disregarded this and we have just considered the core and we have taken its eigenfunctions. This is what we have done, and its eigenvalues were what gave me the previous eigenvalues, energy states. But remember that this is present. So, instead of taking this side, we are taking this, which is eigenfunction of the core. But this is there. So, what will happen is that this term will introduce mixing in these various phi. And this is the concept of configuration mixing. So, each pure configuration will mix. Now, regarding the mixing, you must understand that the nucleus is an isolated system. It is not under the effect of magnetic field during this entire thing. It is just sitting idle. Right now, the nuclei in my hand, in this chalk and everywhere else, they are just sitting idle. There is not much magnetic field or anything electric field out there for it to interact. So, if nucleus is an isolated system, then the angular momentum will be conserved. Right? So, the mixing that will happen because of this H1 will be between the mixing between the same J states, same angular momentum states. Okay? Same angular momentum states. Write this down, these all things later on. This is the basic idea behind configuration mixing, behind all the mathematics that we have done till now. Okay, so now what? So basically, because of the effect of configuration mixing, different J will mix. So now, instead of just considering the 1d 5 half, let me also consider the 2s half as well. So you see, if the two neutrons are in 2s half, I have also shown this. So the possible angular momentum is only 0. And then above 1d 3 half, possible angular momentum is 0 and 2. So you see, just from these 3 levels, we have got 3 0 plus states. Right? So now what we will do, we will again do the same old calculations, but now this time we will consider the mixing between the various 0 plus states. And this is what I have done in my previous class, the 2-level mixing problem. The 0 plus states. So this is what we have done. And you will be amazed to know that as a result of configuration mixing, so this is without config mixing, just plus pairing, okay, and this is with config mixing plus pairing. You will see that the results are now much closer to the experiment, but they are not entirely the same. Why? Because still now we have just taken the model space to be d5 half, 2s half, d3 half. If we take even more model space, then the result will become much better. So you see, the entire thing depends not only on the pairing stuff but also on the model space and the configuration mixing. So this is how actual real shell model calculations are done. Where you see, just for this 0 plus case, I have considered a 3 by 3 matrix to be diagonalized for configuration mixing. In real shell model calculations, if you consider a very large model space, then you might have to diagonalize 1 lakh by 1 lakh matrix, all 0 plus states. Now it becomes very difficult. It becomes very difficult. And so we need a lot of computational power, and also the effective interaction has to be important. This is also another very important part. It has to be taken into account. Otherwise, we will not be able to reproduce the effect of the real experimental result. Now, you see, in reality, the nucleon-nucleon force interaction, it does have a repulsive code, right? But here you see, in order to reproduce the experiment, we will be considering not the real interaction but a sort of effective interaction which will be model dependent. What model dependent? Basically, if I take a very small model space, my effective interaction will be different to reproduce the experimental spectra. If I take a larger model space, my effective interaction will again be different. So, model space and correspondingly effective interaction, they will both be changing. So, I have introduced and discussed a lot of concepts. But again, this is not all. So, still now we are just talking about the fact that proton and neutron are interacting, but still they are filling the levels independently. Now we move on to the next topic. So now the difference in Coulomb interaction, let us try to address this point using the isospin quantum number. Again, we now introduce the T concept, isospin. So you see, proton and neutron, one has no charge, another has positive charge. Now this is very similar to the spin plus half minus half case, right? So we can use the same old spinor concept and introduce the isospin. There we have spin, here we will have isospin. So same spin concepts, and we will introduce the concept of isospin, and as a result the entire discussion here we are just discussing the whole thing entirely for proton, entirely for neutron. But now we will be compacting the both protons and neutrons together using the concept of isospin. So then the next part, again the protons and neutrons are interacting, residual interaction is there, but because of using the isospin, now they will be filling the levels together, and we will not consider the proton and neutron independently. So we will just consider a nucleon with isospin quantum number, either Tz plus half or Tz minus half. That's all. So this is a rough idea of how the shell model calculations are done from very basic to advanced scenarios. Again, there are a lot of many other concepts. I will tell you about it later on. But this fact is very important. Remember, the very basic ideas of starting from 18 oxygen. This is a very nice, very simple case which illustrates so many things. The very fact that it has got 3 levels, it means the presence of residual interaction. The very fact that even using the pairing, you just can't reproduce this fact. The level means the presence of configuration mixing. So you see, this thing here, the effect of both configuration and pairing is there. Otherwise, you will not be able to reproduce the experimental spectra. And so, residual interactions manifestations are both pairing interaction as well as configuration mixing. বুঝতে পারলে? Any questions? বলো। এগুলো লিখে নেবে কিন্তু।